Good afternoon, gentlemen. The topic for discussion today is fuel oil system, and this is the most important system on a ship, because the fuel oil system on a ship determines how efficiently the company is able to manage its cost. Okay, to the extent that the fuel oil cost for every ship accounts for nearly 60% of the operating cost of a ship. Hence, this system needs to be looked at very carefully, and all shipping companies take note of the fuel oil systems and the accuracy and effectiveness of the system. So let's take a kind of a dive into what we are talking about. So we are talking of, let's say, a engine which is going to be in operation. So we will, before I really dive into the main topic, which will be Doxford engine and the common system, I will first establish what are the major requirements for any fuel oil system, irrespective of whatever it is. It could be petrol engine, diesel engine, whatever engine, right? So let's look at the 6 important things that one would need to address when you're talking about a fuel oil system. Right, the fuel oil system needs to meter the quantity of fuel which is being injected into to each cylinder of an engine. Let's assume that we have an engine with 6 cylinders. So then we are looking at oil supply to each one of these cylinders, right? So the most important thing in this case is metering the quantity being supplied. Please remember that metering means the quantity which you inject in every particular stroke of the ship, right? Let's assume that the metering, let's say the engine is running at, let's say, 100 rpm. So 100 times the crankshaft is rotating per minute, and multiplied by 60 minutes into 24 hours into n number of days is the fuel oil consumption of a ship. Let's assume there is a 5% error, which means the consumption is high. Then imagine yourself, this small increase could result in a huge amount of extra dollars or expenditure to the ship. Hence, the metering system for every ship is of great and prime importance. The technical superintendents particularly are very concerned about the fuel consumption of every ship. Next, the next important thing that a fuel oil system should be able to do is the fuel oil timing. The fuel oil is injected somewhere slightly before TDC, and it continues till it crosses about, let's say, 15 degrees TDC. So effectively, the fuel which needs to be delivered is delivered about 5 or 8 degrees before TDC, and it continues for another 15 degrees on the other side after TDC. So this timing is very crucial, because if you do not inject it at the right time, at the right place, then you could either have excess fuel being delivered, or there could be what I would call as after burning and black exhaust. So a fuel oil system should be able to correctly deliver the appropriate pressure so that the fuel injector can be allowed to open, and it should be able to deliver at the right point of the cycle. A little on either side will change the power generated by the engine. So the timing is of great importance, right? That is the point number 2. The next point that I would like to talk about would be what is called as the atomization and the penetration of fuel oil in a system. So whenever we are delivering fuel oil, we are going to what is called as atomize the fuel. Atomization means you break the fuel particles into as many small particles as possible, so that the particles can be delivered very efficiently and correctly into the engine cylinder. This will result in good quality combustion, and thereby the engine will generate the power expected from it without any penalty on extra fuel consumption. If the atomization is not good, then the quality of the fuel that gets burned will be rather poor. So it is important that the particles are able to get atomized. So the next question comes, I am spraying oil into the cylinder, then how does actually the particle ignite, which means Is there an external source of ignition which is provided? No. In the case of diesel engines, we have what is called as a temperature of around 500 to 600 degrees centigrade. This temperature range at the end of compression again. So this temperature range is the ideal temperature for what is called as auto ignition, which means that when you compress the air in the cylinder, the compressed air, let's say at 100 bar pressure, is now at a temperature of close to 600 degrees centigrade and more. So this temperature is ideally the auto ignition temperature for the fuel being used, which is in this case the fuel oil which is being sprayed into the cylinder. So the atomization being very essential. The next point which we need to take into account is called penetration. Now let's understand what is penetration. The penetration is the extent to which the fuel will get sprayed into the cylinder, and thereby the fuel gets distributed properly and evenly in the combustion chamber. Now, few key things are very important. If the penetration is too high, then the combustion, the fuel particles may hit the walls of the liner, and this would result in excessive burning of the fuel on the liner walls. If the fuel burns on the liner walls, the cylinder oil will get burned, which means there will be metal to metal friction between the piston rings and the liner. That is something that we want to avoid. If the penetration is too less, then the oil will be sprayed inside the combustion chamber in a small zone near the nozzle tip. If the combustion starts very close to the nozzle tip will get hot and it may fail, which means the fuel injector would fail. Otherwise, the combustion, the power that is delivered by the cylinder because of combustion very close to the tip may not be enough to push the cylinder down and thereby generate work. So, so far we have covered 4 topics. One is called as metering, the quantity of fuel to be delivered per cylinder. Next, the timing. It's absolutely essential that the timing for injection goes well. Next point is atomization, which means the tiniest particle to which the oil can be broken while it is being sprayed into the cylinder. The fourth point being penetration. As a thumb rule, it is often expected that the spray cone which is coming out of the injector should lie in the range of 0.6 times the diameter of the liner. So if it is in this range, then the fuel starts igniting, is able to catch fire and deliver the appropriate power that is required of the cylinder. The point number 5, the admission should be regulated in relation to the combustion pressure. Right. Let's look at an engine and let's assume that the MCR, at the MCR RPM, you are able to generate about 180 bar pressure on the cylinder. The overloads power of an engine, let's say, is about 190 bar pressure. Suppose the engine is at a continuous service rating, and if for some reason the peak pressure generated because of the fuel quality being having higher calorific value increases the peak pressure, then what are the consequences? If the peak pressure is lesser than required, obviously the power is less. However, if the peak pressure is way beyond what is being designed, then you will ask for trouble. Now, what is the trouble? Let's understand this. If the peak pressure rises, then that the combustion chamber components, which are actually the combustion chamber components, are the liner, the piston ring, and the piston. Now, if too much pressure falls on the piston ring, it becomes like a weak link. There are 4 piston rings there on the piston. So the piston ring may collapse or get seized or get damaged. On the other hand, if the peak pressure rises, then there is increase in the mechanical load on the engine, which means that the extra pressure would relate in F is equal to P into A, which means pressure into area. The force that is delivered onto the crosshead, the crosshead guides, the bottom end bearing and main bearing increases. If the engine's components like the bearings are not designed for it, you will have possibly what is called as an engine failure. So that is the reason why we need to make sure that the fuel is delivered at the most desirable point, but at the same time the peak pressure should not be allowed to increase. Then the last point which I would like to emphasize is the proper starting and termination of injection. Now this is very key. Normally fuel systems are so designed that the pressure which is supposed to be delivered gets generated very quickly as the fuel pump starts working and the pressure is transmitted to the atomizing nozzle. Now if the nozzle starts spraying and once you have decided at what point you want to terminate, the termination should happen in a snappy manner, which means that when the end of termination is expected, the termination should happen that. There cannot be a scope for after burning or dribbling, which means after the main spray is being done, there cannot be a secondary spray or dribbling of the nozzle tip. This, if it happens, will cause afterburning and possibly damage to the exhaust boiler, the turbocharger, the peak pressures and the exhaust temperatures will shoot up, resulting in damage to the engine components. So you definitely don't want a secondary injection during every firing cycle. So these are generally the broad requirements that one would expect from the fuel oil system. Now let's look at some fundamentals about the type of injection system we are talking about. In general, the injection systems broadly get classified under two categories. One is called the air injection system and the other one is called airless injection. The air injection system generally uses a very simple concept. The air injection system is of course outdated by more than 100 years, so it no more exists. But however, we need to understand history so that we don't repeat historical mistakes. Right? The air injection system believed in a very simple concept. You either use coal as fuel or you could use even oil. But there were limitations to the air injection system. I'll explain that. So here the system works this way. You have an air bottle filled with, let's say, 30 bar pressure. You take that air and then you use that air to spray the fuel into the combustion chamber when the piston is close to the TDC. Now there are limitations. If 30 bar is the pressure of the air, then if the air has to enter a combustion chamber which is already under compression, having compressed air, then the pressure of the chamber, whatever pressure is developed, which is called the compression pressure, cannot be more than 30 bar, which means that I must generate close to 20 bar pressure only as compression pressure. This is a serious limitation. And the other challenge is air cannot necessarily be expected to finely break and distribute the particles. So the early part of the last century, which is 1900s, and until the First World War, the industry was struggling with this air injection system. One thing that they realized is they are going the wrong route, and this cannot be the long-term solution. So Rudolf Diesel then said, okay, I need to rework how this system works. Hence, we will have to look at an alternative platform or concept for distribution of fuel inside a diesel cycle cylinder. So then came the concept of solid injection or airless injection. Airless injection means you will not be using air, compressed air from the air bottle for injection, right? So let's just recap what air injection was. Operating principle as designed by Rudolf Diesel, you had fuel oil metering. The fuel is brought to the atomizer and compressed air is used to break up the fuel into smaller particles. Injection occurred when the nozzle valve opened. The fuel injector is actuated by a can. High pressure air then finally breaks the particle into particles. So what they realized was the power generated in this air injection system is not good enough for powering large sea-going ships. Then they realized that they have to go in for airless injection, right? So for the airless injection, there are three models that have been developed historically. The first model is called common rail system. The second model is called unit injection system, and the last one is called gas compression system. In this module, I will be talking largely or only about the common rail system. Okay, so the common rail system let's understand what this system is all about. The manufacturer who actually came out with this common rail system and popularized it in the first part of the century, the previous century I mean, 1900s until mid-90s etc., largely was Doxford. They were the kings, they were the queens. There was hardly any competition from the now big boys, which is called MAN, BMW and Sulzer Vatsila, right? So Doxford ruled the roost, and they had come out with an injection system which is called by principle a common rail. So what Doxford for the fuel system did was, they used to have a pump, a reciprocating pump, which is engine driven, I repeat, and it will pump oil into what is called as a common manifold or a common rail. Now from the common rail, the fuel needed to be injected into the cylinder. So what I am going to discuss in this module is how this fuel gets delivered into the cylinders. Okay, whenever you talk of any hydraulic system, you must remember that there is one default item which should always be there, that is called an accumulator bottle, which means that the accumulator will always be part of any hydraulic system. So let's dive a little deeper into the system. So here you see a diagram and you have a Doxford engine fuel system. Let's look at what is happening in the system to understand it a little better. What you see here on the left hand bottom side is that the engine driven pump is a reciprocating pump, and there is a pump, and then you will find that there is a long pipe going up, and there is an accumulator bottle, and there is what is called as a fuel timing valve block. Now there is one pump for each unit that you have. Let's say you have 6 units, you will have 6 pump blocks which are mounted. The pump blocks have a plunger running inside them, which is actually developing the pressure. The plunger is connected to what is called as a rack, and the rack is governed, for each unit is governed through a common lever which is called the governor control lever. Okay, so that's the bottom part of the diagram. There you will also find the diagram, that is an oil inlet and there is a pipe which is going, which is called the manifold or common pipe, which is traveling up past the accumulator bottle. Now what we are trying to do here is, we are trying to inject fuel through the injector needle valves, which is on the right side of the diagram, right side top, right? So what we are aiming is, we need to, for each cylinder, time the injection in such a manner that when I want, at the most appropriate time, I should be able to deliver the quantity inside the cylinder without compromising on the load and other parameters, right? So let's look at how this is achieved. You have a pump, a set of pumps which are being driven by the engine, and there is a common rack for each. So the oil comes into the manifold and the valve timing block is there. So the valve timing block has got a set of 2 valves. There is a valve at the top and there is a valve at the bottom. Underneath the valve timing block, you have a piece called a push rod. The push rod is mounted on a forked lever, on a lever, and that lever on one side is mounted on a fulcrum that you see on the right side center, and the lever on the other side is riding on what is called as the camshaft. So the on the camshaft, where the lever is resting, you will also find a roller. So while the engine is running, the roller is riding on the camshaft, and let's see how the fuel timing is achieved. Okay, so on the right side you will find, at the bottom you will find that there is a valve lifting here. This is your control lever, which is your maneuvering handle lever. So let's see how the injection is being timed. In the fuel timing block, you will also find a valve which is shown at the bottom. Okay, so what we are trying to do is, we are sending about 500 bar pressure through past the accumulator bottle onto the top valve. The valve opens and then the oil collects in the center chamber. Now we need to open the bottom valve, which will be called technically the start of injection. Now how do we time it, right? So for this cylinder, depending on the RPM that you are maintaining, which means dead slow, whatever RPM you have, the fulcrum, which is on the right side center, will move either up or down depending on what it is. So for a given speed, it will continue to be at its position, but when you are varying the speed, this will move. So when the fulcrum moves, the cam which is riding the roller which is riding the cam will lift the lever. When the lever lifts, the push rod lifts. Now, when the push rod lifts, it will also lift at one particular time the valve. When the valve lifts, the fuel oil is then sent from this past this valve, and it is ready to be injected into the engine cylinder. So that is how you actually achieve timing. Okay. So the commencement is happening the moment the lower valve is lifted and the fuel rushes into the high pressure pipes ready to be delivered through the needle valve. So that's your basics of your Doxford engine. Going further, as I told you, there is an air bottle, there is an accumulator bottle. Let's understand its role. The accumulator bottle pre-charges the fuel oil system to about 140 bars. So when, let's say that the engine is about to start. Okay, so let's say that the fuel oil system, the engine is stopped. So when you want to start the engine, you will start the priming pump. The priming pump will immediately get a boost pressure of 140 bar, and the engine is ready for its action. Okay. So as I mentioned to you, the opening of the lower valve is start of injection. Please remember that this engine has one kind of a limitation. The stop of injection is controlled by the roller riding off the cam as the cam moves in the clockwise direction, which means I can only control the start of injection, but I am not able to control the end of injection. That is the kind of a limitation that can be overcome with some of the mechanisms. But in the diagram shown, that remains a limitation. Right? So, given that the stop of injection is not controllable, then the question is, how do I maintain various speeds and RPM of the ship? So the way we do it is, the for lower speeds, much of the fuel gets delivered after TDC, and that kind of becomes a limitation of this engine. However, given the limitations, it has been a very popular model, and the industry in the first part of the previous century at least, most of the passenger ships, most of the cargo ships and ocean going ships were using this. Pretty effective engine and quite effective. Right now, I think this engine is part of the Jurassic Park. Out of this engine came one very important concept called common rail. This common rail, as I say, history tends to repeat, was later on copied by BMW and Sulzer, and they, for their new intelligent engines, are using common rail concept to drive a number of components for accurate metering and timing of the engine. Thank you, gentlemen.